some graphs. Just a minute. All right. Can you view my screen? Yeah, please say it, because I mean I don't see that chats when I go into the different screen. All right, so let me remove this one. So yeah, anyway, so let us look at the following thing. X. So these are few fundamental polynomials. I mean, the polynomials which play a fundamental role to study the behavior of the function. Of course, this is a line y equal to x, and let's look at x square, right? So you see here the x-axis become tangent here, all right, and both side goes upward, right? So similarly, if you look at x cube, these things you know actually, but still I'm repeating this because this actually the model for the behavior. Okay, mainly these two. I'll put x to the power 4 also. Okay. All right. So see the point here, x cube has a different behavior, right? Apart from, so x and x cube are quite similar behavior, and x square and x4 are similar behavior, right? Have the similar behavior at the point, around the point x equal to 0. So this is important, keep in mind. All right. that is today's 16. What's going on? Oh, it works. Right. Okay, so today is 16th. All right, so let me give few exercise before I proceed further. So expand as expanding Taylor's formula up to the order n. So which means n plus 1. Taylor polynomial will be degree n. So 1 fx is equal to sine. This is irritating. To fx is log 1 plus x greater than minus 1 at the origin. This app got updated and it's problem at the origin. Third, fx equal to x to the power n plus 1 mod x. Okay. Now let's come to the following question. What? Behaviors of the function are determined by the second derivative. So now f is a function. Suppose f is a function from, let's say, open interval AB to R, and the first derivative. What kind of information for the first derivative gives us? Can you say that? What kind of information can you get from the first derivative?
It's increasing or decreasing.
And anything more?
Maxima minima, local maxima minima.
Well, local maximum minima we don't get exactly, right? We get the points. There might be maximum minima, right? There might be, but there are points where it may not have maximum minima. For example, this fx. So example to remind is fx equal to x square, right? Fx equal to x cube, right? Here 0 is a point of local mean, my god, it's not working. So let me try with the other version. This got upgraded, and this has this kind of problems. Let me see. Try this, the older one. No, even this will work. Okay. Okay, this is better. Oh, it came. Good. All right. So fx equal. This is the point of. Let me see it works. Yeah, it's working. Zero is a point of local mean. No local max or mean at x equal to 0, right? So, but derivative f prime 0 is 0 here, and here also f prime 0 is 0, right? So first derivative, what does first derivative determines? What does the first derivative determines about the function? So this is when when f prime is not equal to 0, nowhere vanishing in a neighborhood of a point x naught, we get yes. Let me trust. Uh, uh, when a prime nowhere vanishing in the neighborhood of a point x naught, we get whether we get the information whether f is increasing or decreasing in both the cases. We have local, we have that, we get that f is locally, f is actually invertible on that neighborhood. All right, so we get this one, and if f prime x naught equal to 0, then we know that this is a complicated point. So, which means the mathematical notion is singularity. So here, many things can happen. There might be max or mean. There might not might not have any particular behavior. So for example, here, second one, as an example, you can consider fx equal to x square sine 1 over x when x not equal to 0 and 0 when x equal to 0. Right? And let's check in the graph what happens, what is given by this function. Let me see if, let us see if anything can be seen from there. Let me save this. Oh my god, I need to sign in. So clear on. So x square, then sine, oh, no, I don't want on top of it. X square sine 1 by x. See the complicated stuff here. Could you see it? As you go smaller and smaller, this wave-like things will get unfolded and unfolded. And this as you see here, it's not exactly a line. It's like this, but somehow it becomes differentiable at 0. So you, in any neighborhood of 0, you don't get any particular behavior. You see here, sometimes it is increasing, sometimes it is decreasing, right? Could you see this?
Yes.
You see, it is as you go zoom in, it will be the same behavior all the time, like this. But of course, this kind of, I mean, this is a behavior which cannot be studied as such. This is not a standard behavior, right? So it is neither increasing nor decreasing. Right. So this is complicated. So many things can happen there. So when this derivative is 0, many things can happen. All right. So now we go to this question of second derivative. So second derivative. All right. Now this is very interesting. You will see that actually the maxima, minima, it's not as so you have seen in school or in first year maybe that maximum and minimum can be determined by the first derivative and the second derivative, right? If the second derivative is non-zero.
Yes, sir.
Have you seen this?
Yes, sir.
Yeah. So that this is not actually an isolated phenomenon. It is actually a, a part of global phenomenon, which will come now, and that's what we get using the Taylor's formula. All right. So few definitions first. Well, before definition, let me draw a picture. That would be good. So let me draw. Right. This is x-axis. This is y-axis. And suppose The curve is like this. No, I'll take a different color for the curve. So consider this, right? This is the graph of fx. The corresponding to x, you have fx. Maybe I should put a little bit here. Something like this, yes. All right. So you see here, now let me draw tangents. Look at the tangent here, it will be something like this. Right? If we look at tangent here, it will be something like this. Right? You look at tangent here, something like this. So the interesting point here is that, so call this the point x1, this point as x2, and this point as x3. So do you see three different behavior here of the graph? And of course, with respect to the tangent line. Yeah. Maybe I should draw this part a little more carefully. Right. So what is the three things that I'm saying here? So that is, here at this point, the graph. So this is all points x comma fx. So graph of fx. So this is graph of f. So the graph lies below the tangent line. right here. Graph lies below the tangent line. Of course, in a neighborhood. If you go this way, go infinite, you will hit the graph again. But what happens? We want actually locally. So, in a neighborhood. And here, what happens here? The graph lies above the tangent line. Right? And here, on one side, it lies, graph lies above the tangent line, and on the other side, the graph lies below the tangent line. Right? So here the graph lies above, and here it lies below. Is this clear? So these three different behavior. Is it?
So,
Yes.
so in the x1 point, so, I think it should not be a tangent because if the line intersects the curve, then it should be an intersect.
Really? Let's look at a graph. See, instead of this one, let's look at yeah. What happened? Oh, see. Do you see it? What is the x-axis? Here.
Okay, no, yes, sir, yes.
Yeah. So this can happen that it is tangent. So it intersects, but it can intersect tangentially.
Okay, sir.
All right. So that is what here the behavior, and this point is kind of x square behavior, not x square minus x square, and this downwards will be some x power 2m type of behavior, x square type behavior. So these three are these three behavior clear? So we are going to define three notion here. So this is this is called convex upward. So having tangent line, having the graph below the tangent line in a neighborhood. Here, this is called convex downwards. Downward. And this is point of inflection. Okay. Are these terms clear? So one is convex upward, other is convex downward, and other is point of inflection. Now, if you want to define it is precisely, we can do so. So we just define definition this terms, whatever I said. Graph of a function, graph of a function is said to be convex downward if at a point x naught, function f, let's say f is defined, let's assume f is defined on the whole of R. If there exists delta greater than 0 such that the tangent line to the curve to the graph at x naught lies and is missing. Lies what do I say? Lies below the graph on x naught minus delta to x naught plus delta. Right? So similarly, one can define convex upward if there exists delta greater than 0 such that the graph or the tangent line to the graph at x naught lies above the graph. So above the graph here, this point, you have to exclude the point x naught. At x naught, they are equal. Lies above the graph on x naught minus delta to x naught plus delta minus the point x naught. So this is the picture. This is convex upward. So at the point x naught, the x2, these two are equal. Other points, they are not equal. Though the picture looks like they are touching, but they are touching only at one point. That is definitely clear for all of you. All right. And third one is point of inflection. So point of inflection x0 is a point of inflection if there exists delta greater than 0 such that the curve or the graph lies on one side of the tangent line for all x in x0 minus delta to x0, and the graph lies on the other side of the tangent line for all x belongs to x0 minus delta to x0. So these are three concepts. So in fact, I can tell you one more concept which actually comes from this one. So the graph lies. So this picture, like y equal to x square. So
Sir, one thing.
yeah,
Sir, are these three possibilities exhaustive? Like a function has to be one of these three?
yeah. So we already have an example. These are not. This is not exhaustive. As exhaustive, right? So what is the example?
Oh, x squared
Yeah.
by x at x is 0.
Right. So this one, right? This is you don't get any of this behavior
Yeah, right, sir.
from this one. Yes. All right. So this perhaps you have seen some, calculus course or some, if you read more about calculus, but this is actually what the second derivative determines. So this picture, this is graph of f. If this is the picture, take 2 points and line joining this two lies up above the graph, then this function, line joining these 2 points, let's say this is x1 and this is x2, then line joining x1 and x1 comma fx1 and x2 comma fx2 is this one. So any point in the line will be t times fx1 plus 1 minus t times fx2. Any point will be of this form, and this is bigger than the functional value here, right? And this point will be tx1 plus 1 minus t x2, right? So this will be less or equal to f of tx1 plus 1 minus t x2. So if this holds for all x1 x2 x1 is to whatever where f is defined. So let's take f is defined ab to r for all x1 x2 in r in ab, and for all t belongs to 0 1, then f is said to be convex. So this is the definition of convex function. The interesting property for those who are interested, this is a remark we can prove, try to prove. A convex function, we don't need derivative for that, for the definition. On an open interval is continuous. Anyway, I will not go details into this convex function, but what I want is the similarity of this one with convex downward, right? So there is, if the function is differentiable, then convex downwards will give you the convex function. All right, so let's go to the behavior of the function. Here is a theorem. If a function f has continuous second derivative on, let's say, an open interval AB, and f double prime x naught is greater than 0 for x naught belongs to, for some x naught belongs to AB, then the graph of f, what will be the behavior? Is convex
Downwards.
upward, downwards, right? Convex downward at x equal to x naught. Right? So did I put in the definition upward at x equal to x naught? Convex downward at a point x naught. Yeah. Right. The proof is very simple. So this is the behavior. This is the behavior of what we actually expect to get, and this will determine maxima, in particular when the derivative, first derivative becomes 0. Right? So convex downward and the derivative 0 gives you the maximum, right? No, sorry, minimum. Isn't it? So derivative 0 means the tangent line is parallel to x-axis at some point. This is not the right one. So then this is also not happening. Right. Something like this. The tangent, so derivative 0 means tangent parallel to x-axis and double derivative greater than 0, right? That will give you the maximum because it's convex downwards, something like this, right? So let's go to the proof. We'll remark later. So how to go through proof? Proof is we will use. Sorry. We will use the Taylor's formula. Taylor's formula. And we'll use, of course, Taylor's formula with Lagrange's form of remainder. Remainder doesn't matter that much. Yeah, with Lagrange's form of remainder, actually. Form of remainder. Yeah, it does matter, actually. So this will play important. Now, how many derivatives I'll get the past Taylor series, Taylor formula? Till how many derivatives?
Two.
The remainder term will have the second derivative. We don't know whether it has the third derivative or not. So the remainder term will have double derivative. So the order of the Taylor's formula will be 1. So Taylor polynomial will be of degree 1. So fx will be f of x naught at x naught at x equal to x naught, right? So f of x naught plus x minus x naught f prime x naught plus remainder term. What is the remainder term? Where Rx is x minus x naught square by 2 f double prime. C lies between x and x naught, which we can write as what? X naught plus theta times x minus x naught, which is nothing but the formalism here. This one, tx1 plus 1 minus tx2. This is what? Theta x plus 1 minus theta x naught for some theta belongs to 0, 1. All right. Now what we need is, so this is note. We note that y equal to fx naught plus x minus x naught f prime x naught is the equation of the tangent line to the graph of f at x equal to x naught, right? So this is the tangent line. If you draw the picture, right? So if this is the point here, x naught, and you see here This is the tangent line, and this is the graph. So remainder term is the difference between these two. We don't know whether graph might be down there or up. We don't know. But now we'll see.
So there should be a 1 minus theta as well, right, in the remainder term.
Oh no, here this is fine, right? We are looking at Lagrange's form of remainder, right? This is f double prime c.
Wasn't there a 1 minus theta as well, multiplied with the...
No, that was in Cauchy's form of remainder. Let's look at again. See here. Here, see, this is it. The first one is the Lagrange's form of remainder, and second one is Cauchy's form of remainder. All right.
Oh, okay. Yes, sir.
First one doesn't have any 1 minus theta.
Right.
All right. So now we'll compare. So what is, whether this curve lies below or above the tangent line, it will be determined by the remainder term. So since f double prime x naught is, what was the assumption? Greater than 0. Greater than 0, and f double prime is continuous, there exists delta greater than 0 such that f double prime x is greater than 0 for all x in x naught minus delta to x naught plus delta. All right. So this is true by continuity of f double prime. Now look at remainder term. Now we look at the remainder term. Rx, which is x minus x naught square by 2 f double prime x naught plus theta times x minus x naught for some theta belongs to 0, 1. Now this part is greater than 0, right? In a neighborhood of x naught, and which means for any theta here, as long as x lies in a small neighborhood of x naught, this is fine. Now look at this one. So do you get the similarity of this function with fx equal to x square? Right? So this part is greater than 0, greater than equal to 0 for all x, actually strictly greater than 0 for all x belongs to x naught minus delta to x naught plus delta minus the point x naught. All right. So this implies Rx is greater or equal to 0. So which means, and greater or equal to 0, of course, and actually what I need is strictly greater than 0 on x naught minus delta, x naught plus delta minus the point x naught. So this implies what? fx, which is fx naught plus x minus x naught f prime x naught plus rx is greater than fx naught plus x minus x naught f prime x naught, right? For all x in x minus x naught minus delta to x naught plus delta minus the point x naught. This means if the graph of f, the graph of f is convex downwards, right? Convex downward. Is this fine? Is this fine? So graph will lie on the top of the tangent line in a small neighborhood. Yeah, somebody was saying something. All right. So similarly, when f prime, f double prime x naught is less than 0, you can show that f is convex upward at the point here, right? And next time we'll see tomorrow, when the second derivative also 0, then what happens? All right. Any question? Any question? Okay, if you have no question, and so your tutors must be waiting to explain
Excuse me, sir.
something. Yes.
Sir,
Okay.
is this a if and only if condition?
Which one?
So that if being convex down implies if double dash is greater than 0.
That is not true, because I mean you need the differentiability also, right?
Okay, sir. And if we have differentiability,
If we assume differentiability, then the convex downward is actually, yeah, that would be if and only. So if we have enough differentiability at that point, yeah, that is true. So why don't you can just check and let me know tomorrow that whether this is actually true. Actually, this is true, because I mean, you see, what is the convex downward? You will see it will be all the time upward. Uh, that is true, and you have enough differentiability. No, 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 no. The point is there might be problems, because no, sorry. Here is one thing that might occur. Yeah, yeah. I'm sorry, extremely sorry. So here is one thing that might occur. So for example, this is x-axis, this is y-axis. You can make this one enough smooth to touch here. And you can make enough smooth to touch here. Okay. And this part, and here it will be just line. So at this point, all the derivative will vanish. The function will be constant 0. It will be possible to construct. We'll show that. Okay, do you see it?
yes, sir.
Yeah, so you can make this one enough smooth so that it does not look like there is a bump or something here. I mean, there is no, yeah, you can make it enough smooth. Even whatever smooth you want, you can make. Infinitely smooth you can make here. I mean, infinitely differentiable at this point, and still have this property. So in this case, derivative will be always 0, and you will see this is convex upward. Right? Well, actually, what did I say? Convex upward? Yeah, actually, if you look at the derivative, yeah. So let me go to the definition part here. So yeah, convex downward is something like this. See here, tangent lies below the graph. I mean, if you look at this one as a strict one, strictly below, then you are right, it will be if and only if. But if you also give that equality over there, then it will not be right. Okay. So tangent might exist here at one point, but there might be graph such that the tangent line is actually equal to the graph there. So that part we have not mentioned. So here, I mean, if you look at just below, see below is not the right word here. Below on this, because at x naught they are equal. So the equality is considered here. It means it can be up to the graph. In that case, that the condition what we proved is not if and only if. So that would be a counter example. This kind of examples will be counter examples to this. All right.
Yes, sir.
Yeah. Any other question? Okay, then I'll see you tomorrow again.